It's 1 o'clock, so we'll start. Thanks for joining, everyone. I see there's a few attendees joining in the last couple of minutes, so hopefully more will join in. I'll kick this off by doing a bit of an introduction, and then I'll hand the microphone over to the three presenters. So this is the 45th webinar for Australian chapter of the IGS. And here we are lucky enough to have three of the best presenters from GeoAsia8 in 2025, which happened in Brisbane earlier this year. So the first presenter is Ashray, the second presenter is Nastiti, third presenter is Sarika. So just a little bit of a background on IGS. IGS is a global organization that promotes the advocacy of geosynthetics. There's 45 chapters globally with over 4,000 members, as you can see in this map. And there's a number of benefits for joining IGS in case you're not currently a IGS member, specifically for young professionals. If you're a student, PhD or postgraduate or undergraduate, you can join for free for ACIGS, and there's a number of benefits associated with that. For example, the next slide, we have a job shadowing program. That job shadowing program allows you to come to a workplace and spend a day with a professional or multiple professionals, just to understand how people in the workplace work. So that could be a scientist, that could be a manufacturer, that could be a engineering or a scientific company. There's a number of different opportunities there. So if you're interested, jump on the website and lodge your interest. Similarly, we have a summer internship program. The summer internship program lasts for 10 to 12 weeks. It's you get a small stipend, so a small kind of payment from ACIGS, and you get to spend, full time at one of these many companies, either installer or a manufacturer or a R&D facility or a lab. But there's such a large representation in the geosynthetics sector or engineering company, and you get first-hand experience by doing some actual work. So if you're interested in that, if you're looking for a summer internship, at the end of this year, please apply. Go online or to www.acigs.org and follow the links to the summer internship and just fill out the form. And you have to be a student. You have to have a student membership, and the student membership's free. So please get along if you're interested in getting some professional experience. So this is a quick introduction to Ashray, our first presenter. So Ashray is a fifth-year PhD candidate in civil engineering at the University of Texas at Austin, specializing in transportation geotechnics. He completed his bachelor's degree in civil engineering from Al-Ghai Muslim University, where he worked on environmental sustainability projects focusing on waste management and green infrastructure. For his master's degree at IIT Chandigarh, Ashray studied the mechanical behaviors of geomaterials, specifically using biofilm or biopolymers for fly ash stabilisation, and graduated as the gold medalist of the civil engineering department. So Ashray, if you can share your screen now and kick it off. Thank you.
Thanks, Roger, for the brief introduction, and welcome all the IGS attendees in this meeting. Let me share my screen so that we can proceed from there. All right. Okay, can you see my screen? All right, thank you so much, Roger. All right, good morning, all the attendees who are attending, I would say, from Asia as well as from Australia, and good night to those who are attending from North America. So I'm Asha Saxena, a PhD candidate or a graduate research assistant at University of Texas at Austin. And today I'm going to discuss on the topic of investigations on cracking characteristics of geosynthetic reinforced asphalt using digital image correlation, which is a new technique which we have tried to use in transportation geotechnics work at UT Austin. And hopefully, once you see the results, you will feel that this technique can be used in transportation as well as in geotechnical works that can help us in improving the quality of roads as well as the infrastructure that we currently use in the design of pavement or civil engineering infrastructures. So let me give you a brief introduction, first of all, that what we are going to discuss. But before that, let me ask you a question. I know we are having this meeting online. In person, asking questions are quite different. I can see you all, you can see me, you can see face expressions. But yeah, but just ask you a question that, have you ever used roads in your life? You can answer yourself. And I believe that, of course, you must have used roads in your life. Roads are indeed an integral part of our daily lives, facilitating commutes, travel adventures, as well as basic necessities of our daily lives. You just go out of your home, you will see a road that can help you to reach point destination B just from point A, from your location. So roads are basically the most important part in our daily lives. However, the condition of roads falls short of their expectations. Rutting, potholes, cracks are the common distresses that you can see in these roads. You know, US alone last year spent around $69 billion just for the maintenance of these roads. And according to Sydney Morning Herald report, which is one of the most famous reports from Australia, around 102,000 people gets injured while driving on these roads, which ultimately leads to 1.35 million deaths annually all across the globe, which is a quite big number. And we, as an engineer, have taken this responsibility to reduce this number so that people can save their life. Moreover, people can drive on these roads safely as well as comfortably without causing any issues to the riders. So just to give you a brief idea that what people do when a road is disintegrated or deteriorated. So whenever a road loses its structural capacity, a crack starts appearing on its surface. In order to rehabilitate the road, people don't go for reconstruction. What they generally do, they just put a new layer of road, again, asphalt layer, on top of cracked surface. And if you see this figure, you can clearly see that the cracks which have already been created in existing pavement tries to propagate into the overlay once the load starts coming on the new constructed asphalt overlay or the newly constructed top asphalt surface. So let's say if a pavement is redesigned for 5 to 10 years so that it can improve the lifespan of the pavement by 5 to 10 years, but because of this movement or propagation of cracks from the bottom asphalt layer to the overlay, now your roads fails within 3 years or sometimes even in only 2 years, which cause a lot of problem for transportation engineers, because now they have to reconstruct the road again. Moreover, they have to use a lot of natural resources, which ultimately leads to unsustainability. So the process which actually leads for the propagation of cracks from the bottom asphalt layer to the overlay is called as reflective cracking. This is the term that you might have seen a lot in research articles, as well as you might have heard a lot from transportation engineers who always say that because of reflective cracking, the quality of road has been disintegrated within less time frame that they have actually designed their pavement for. So the motivation of this study actually come after looking into the reflective cracking, which is the major mode of failure. And you know, in order to prevent reflective cracking, a lot of work has been done in the past, which includes you can increase the asphalt layer thickness so that you can delay reflective cracking. You can alter the asphalt mixture compositions, or you can use geosynthetics or paving interlayers between the bottom asphalt layer or the existing pavement layer and the overlay so that you can retard reflective cracking in your pavement. The most common type of geosynthetics which are generally used in asphalt layers includes paving fabric, which is like a geotextile, or paving grid, which is like a geogrid to provide reinforcement. So there are 4 different mechanisms which actually lead to reflective cracking in your overlay. First is, of course, the temperature. Your asphalt is a viscoelastic material which swell and shrink depending on the temperature rise or decrease. So as the temperature increase or decrease, stresses concentrate at the location where the cracks have already been initiated. And once the swelling and shrinking starts in the asphalt layers, they try to create propagation of cracks into the overlay. Similarly, because of the wheel load, let's say when a wheel load is moving on top of your asphalt layer, if you see in the center, what happens when the wheel is approaching the crack, shear stresses are generated at this location. And once the wheel is directly on top of the crack, it leads to bending of your asphalt layer and ultimately leading to bending stresses at the location of the asphalt layer. And finally, as the wheel moves away from the location of your crack, shear stresses again generate in your asphalt layer, which ultimately lead to reflective cracking in your pavement. So people in the past have developed a lot of tests. And in your undergrad, most of you, if you are your undergrad, or whenever you have done your undergrad, you might have heard about 3-point beam test and 4-point beam test, which is the most common test conducted in pavement engineering in order to see the bending stresses at the bottom of the asphalt layer, which ultimately lead to reflective cracking. Similarly, plate load tests have been conducted in the past by a lot of researchers in the field to see how the cracks propagate into the overlay. In addition, direct shear test and interface bond strength test are some of the most common tests to see the benefits provided by geosynthetics in asphalt layers. So people have seen mostly the temperature-induced impact as well as the reflective cracking caused by bending stresses or the flexural loading. But almost no research has seen whether geosynthetics can provide benefits when there is shear loading on your asphalt layers. Because as I showed you in our previous slide, that shear loading happens almost 2 times whenever a single wheel pass on a cracked asphalt layer. So this also plays a very important role in propagation of crack into the overlay, but none of the researchers have looked into it in detail in the past. That's what we are looking in our research in this presentation today. So the research gap that we have found, that limited research has been conducted till now, where shear loads have been applied perpendicular to the reinforcement plane, and the objectives are defined in such a way that a new test setup is developed, which is known as cross shear test setup in this research work that you will see in upcoming slides. The setup was first standardized at different temperatures, strain rates, and interlayer condition, because it's a new test setup which is designed by us. So we wanted to standardize it so that people in the future can use it in their laboratory without worrying about any results or any repeatability issues. But because we have time constraint today, I won't be discussing about how the standardization was performed. We will just deep dive into the results, that how geosynthetics provide benefit in mitigating shear loading. Finally, the test setup is designed in such a way that it can apply direct shear loading on unreinforced as well as geosynthetic reinforced asphalt specimens. The benefits or the main objectives can be defined as that we are looking into, or we are characterizing the benefits provided by geosynthetics when shear loading is applied on the specimens. The cracking resistance potential improvement are defined in geosynthetic reinforced asphalt specimens under monotonic loading. We did test in cyclic loading as well as dynamic loading, but as I told you, because of time constraint, we will be discussing only results under monotonic loading today. And then we will use digital image correlation technique to see what is happening behind the testing that we are doing. So as a researcher, our task not to just see the load displacement curve, our task is to find the mechanisms which are actually leading to the benefits provided by geosynthetics. So that's what our main task is in this study for monotonic loading. So let's move to the experimental program. So as you know that asphalt layers require just two things. First is your aggregate and second is your binder. So the aggregates that we used in this study actually satisfied the XDOT, which is Texas Department of Transportation asphalt mixtures requirement. And the binder that we used was around performance grade PG6422. I know in some countries we still use penetration grade to classify binder, but in US, since performance grade is the most common one, that's why we use PG6422 over there. And then three different types of geosynthetics, which are polyester geograde composite, polyvinyl alcohol geograde composite, and fiberglass geograde composite are used in this study. The properties of these geosynthetics can be found here. As you can see, the ultimate tensile strength of all the products is almost similar. However, the strain at which these materials failed was completely different, which actually affected the stiffness of the products that we have used in this study. And that's why the results are going to be changed that you will see in upcoming slides. Regarding the specimen preparation, everything was prepared in similar way as we generally prepare any asphalt layer in the field. First of all, the bottom asphalt layer was prepared using superpave gyratory compactor, having dimensions of 150 mm by 57 mm, followed by tech coat application and geosynthetic interlayer installation in case of reinforced asphalt specimens. And finally, the top asphalt layer or overlay was constructed on top of it. Since this is the prepared sample, but this sample cannot be used to directly apply shear loading, hence this specimen was trimmed into brick-shaped specimen having dimensions of 150 mm by 76 by 38 mm. And finally, to perform digital image analysis on these specimens, the front face was painted white and then a random speckle pattern using black dots or black color was created on the front face so that the images of this random speckle pattern can be collected and those images can be compared with undeformed image to see that how the stresses and strains are generated in our specimens without even touching the specimen. So this is how the cross shear test setup used to look like. If you see that on the left side, we have a fixed half and on the right side, we have a moving half. So device is designed in such a way that it can apply pure shear loading. Of course, a lot of trial and error has been performed on this setup before calling it as one of the best setup that can be used for evaluating the shear resistance of geosynthetic reinforced asphalt specimens. And those you can read maybe later in one of my paper on standardization. And the trimmed specimen was glued, as you can see, on the right side, as well as on the top side of the right plate and bottom side of the left plate. The left side kept stationary while the right side was allowed to move. The initial sitting load for monotonic loading was kept at 100 Newton, while a constant displacement rate was applied on these specimens at about 7.6 mm per minute. The point of load application was also chosen at about 10 mm away from the center of the specimen. For digital image correlation technique, as you can see here, how the specimen looks with the random speckle pattern on its front face. We used a open software called as DigiCam control software in order to collect images at regular intervals of about 3 seconds. If you want to repeat these tests in your laboratory, you can change the recording time by 1 second as well. The area of interest was chosen in the front face of your specimen. And then a commercialized software called as Vic2D was used to analyze the images. If you are a geotechnical engineer or a transportation engineer and planning to use DIC and you do not have a commercial software available, you can use an open software, which is called as NCore. So there are both open software as well as commercial software available to analyze all these images. In my case, I used a subset size of 19 pixels, a step size of 1, and a strain filter size of 5 pixels. A subset size means that your image is divided into different pixels. And subset size means that the smallest pixel dimensions that you want to compare your deformed images with respect to your undeformed images, so that you can see how much displacement has happened in your deformed images with respect to time or with respect to loading. Now let's move to the results and discussions if you understand what the system is and how the system works. So this is the load displacement curve that any engineer needs in the field. If you see that all the geosynthetics have provided benefits in improving the load carrying capacity, that is improving the shear resistance of the pavement, as well as in delaying the crack initiation in the pavement, that is the resistance at the peak load. And then we use some analytical models to actually verify the benefits provided by these geosynthetics. So these are the analytical models used in this study. And the most important ones are fracture energy and fracture energy index, that how much benefits are provided in terms of improvement in fracture energy index. So these are the results that we have found. If you see, the fracture energy index for control specimen is around 1.7, while for geosynthetic reinforced specimens, it varies from 4.35 to around 8.56. And even if you take just a ratio of 1.71 and 8.56, you will see that the benefit is around 5 times. So 5 times benefit are provided by geosynthetics in terms of improvement in shear resistance. Moreover, if you see the load displacement curves closely, you will see that there is some residual strength provided by the geosynthetics, which you won't see in unreinforced cases. In unreinforced cases, as soon as the crack initiated at the peak load, you will see a sudden drop in the load carrying capacity of your pavement, and hence your pavement becomes unusable. But in case of geosynthetic reinforced asphalt specimens, the benefits are still there once the crack initiated in the pavement. And hence you can take its advantages mostly in the colder climates. When the temperature is super cold, the asphalt is strong but brittle in nature. So in these cases, the asphalt layers crack suddenly, but if they have geosynthetic in it, the cracks is dissipated over a longer period of time. Moreover, even if the crack has initiated, there is some residual strength in your pavement that can take the load coming from the wheels on top of it. If we go to the DIC analysis in order to see the mechanism, what is going behind it, I will show you that this is the area of interest that we have selected on our images. And in our first task was to verify whether the displacement coming out from the DIC analysis as well as from the LVDT, from the laboratory testing, matches well. Because once they matches well, then only we can use this DIC analysis in order to see that how the strains varied in these materials. So these are the 2 points selected on this image directly just below the LVDT in order to verify whether the displacement provided by the images matches with the one provided by the LVDT. And these are the results that we have found. If you see the results provided by the LVDT in the laboratory matches well with the images data. And since in case of images, you won't be touching your specimen, moreover, you can see the behavior of strains on your whole specimen, while in case of LVDT, you will see the behavior of a specimen just at a single location. So these are a lot of benefits that are provided by the digital images, and this task can be carried out on any of your specimen, which is solid in nature. So once we have verified all these images, we went for the analysis of displacement as well as the shear strain contours. So these are some of the reference images. If you see that the length of specimens is defined by vertical bands, the thickness of a specimen is defined by horizontal band, and the part C or the image C is actually defining the shear strain contours in case of undeformed image. And then the images are taken at regular interval of 3 seconds, and those deformed images are compared with this undeformed image, and then shear strain contours are evaluated. So these are the shear strain contours that you can see for all the tested specimens at 9 seconds of monotonic loading. If you see in the shear zone for unreinforced case, you will see that the maximum shear load or the shear strains were generated along the shear plane. While in case of geosynthetic reinforced specimens, you will see that the maximum shear strains are generated along the geosynthetic reinforcement levels. And the geosynthetic is providing benefits, if you see, by providing resistance where there were no shear loads. And if you see the maximum values of the shear strains here as well, you will see that in case of unreinforced specimens, the value is around 3.8%. But in case of reinforced specimens, it varies from 0.9% to 2.8%. So you can see clearly that the shear strain is reduced by so much. And even if you just divide 3.8 by 0.9, you will get around 4.1 or 4.2 times benefit. So which is almost equivalent with the results that we have got from laboratory as well as from analytical model in case of fracture energy index values. So this clearly shows that the benefits provided by geosynthetics are very huge, and moreover, they can delay crack initiation as well as crack propagation. And why I'm showing you the results at 9 seconds of monotonic loading? Because in the next image, the control specimen was broken completely. That's why I'm showing you image all at 9 seconds of monotonic loading. But if you see in reinforced specimens, no crack has been initiated. And if we go to monotonic loading at 21 seconds, you will see that the control specimens are completely fractured. But in case of reinforced specimens, the crack just initiated. So the crack propagation and crack initiation, both things are delayed by the presence of geosynthetics, which is a great benefit provided by these geosynthetics under shear loading. And if you see the crack propagation, you will see that in control specimens, the crack initiated either from top, means the edge of the specimens, or from bottom, and then they try to propagate to the center of your specimen. But in case of reinforced specimens, because maximum shear strains are generated along the geosynthetic location, the cracks initiated at the center location and try to move away from the specimen towards the edge of the specimen. So it has one more benefit, that in case when the crack initiates from the top, moisture infiltrate into your pavement and damages your pavement rapidly. Similarly, if the crack initiated from the bottom of your pavement, the crack goes towards the top of your specimen very quickly and damages your pavement within a short period of time. But when the crack initiates from the center location where geosynthetic is located, now you have enough time to repair your pavement or even to delay the complete failure of your pavement. So these are the benefits which are provided by geosynthetics, and the mechanism that we have found from these images is that geosynthetics mobilize or absorbs the strain coming on them and redistribute them over a wider area, thus provide the benefits in improving the shear resistance of your pavement. So from this study, we can conclude the following points. The cross shear test has demonstrated that all geosynthetic reinforcements have provided benefits in improving the shear resistance of pavement. Among the interlayer used, the polyester geograde composite provided the maximum benefit with a fracture energy index of around 8.56, followed by PVAC and FGC geosynthetic. The DIC technique was found to be effective in defining the mechanism which ultimately lead to the improvement in shear performance of reinforced specimens. In monotonic loading, as we have seen at 9 seconds of loading, the shear strengths were as high as 3.8% in control specimens, while in reinforced specimens, they vary from 0.9 to 2.8% only, providing similar benefits that we have seen in laboratory testing. And the test results indicate that reinforced specimens failed at higher loading time, which means they needed higher displacement in order to fail as well, thus delayed the crack propagation or helped in mobilizing the shear stresses coming on the geosynthetic reinforced specimens. So in summary, we can conclude that geosynthetics provide benefits in improving the shear resistance, and hence they can be used in the future on asphalt layers to improve the structural capacity or to retard reflective cracking in the pavements. So I would like to thank you all for attending this webinar and to And hopefully you will understand something from this slide in this presentation. And I hope if you have any questions, get back to me whenever you get chance. Thank you so much.
Thank you, Ashray. That was very insightful. Just conscious of time, we'll move to the next presenter. And if you have any questions, well, let's hold it to the very end. So I'll quickly share my screen. Can everyone see my screen? No, it's not. Sorry. Oh, you can? Okay. Nastiti is a geotechnical engineer with over a decade of experience in geosynthetics and geotechnical engineering industry. Based in Indonesia, she specializes in soil improvement technologies, geosynthetics design, retaining wall systems, and geotechnical instrumentation. Nastiti holds a degree in geotechnical engineering from the University of Indonesia and currently serves as the research and development manager at Geoforce Indonesia, a leading geosynthetics engineering company in Indonesia. She has been involved in numerous projects across Indonesia, focusing on delivering innovative and sustainable solutions to complex geotechnical challenges in both infrastructure and environmental sectors. Thank you, Nastiti. Continue with the presentation.
Okay, thank you, Roger. I'm going to share my screen first. Okay, can you see my screen, Roger? Okay. Thank you for the opportunity, and good morning from Indonesia because it's 9 a.m. here in Indonesia. So today we are going to have a very quick discussion about the implementation of geosynthetics in hydraulic engineering. To be specific, we are going to talk about the performance of sludge-filled geotextile tubes to overcome muddy coastal abrasion. So basically, this is the things that we are going to discuss today: the project area, the material design, and the construction process, and also the result of this research. So as you may all know, that Indonesia is a very big country consisting of many islands. Approximately 17,000 islands, including major ones like Sumatra, Borneo, Sulawesi, Papua, and Java. And of course, because of that, Indonesia has over 99 kilometers of coastline with combination of sandy, muddy, rock, and also some structures, and almost all of them have a risk of coastal destruction due to abrasion. And because Indonesia is a very big country, I'll focus my research on Java Island, which is one of the most populated island in Indonesia. And we are going to focus on the north coast of Java here, if I can pinpoint here, in Cirebon area. So actually, the north coast of Java is very famous, the North Corridor of Java, because it holds many infrastructure there, from transportation, public infrastructures, power plants, industrial complex, fish ponds, of course, residential area. And as you can see in the right picture, that all of the structure here built on the north coast of Java is actually in danger of abrasion, coastal abrasion. As you can see on the bottom picture, even people's homes are distracted by the abrasion. So how we can overcome this? Especially, as I mentioned before, there are many types of shorelines, especially in muddy coastline, because muddy coastline is well known for its problematic condition, because it consists of soft deposits. So how can we overcome coastal abrasion in muddy coastline? Actually, there are many solutions that you can do. The first one is making structures like seawalls, breakwaters, groins, refacements, or any other structures. And the second one is we can do beach nourishment by replacing lost materials, by adding new materials from outside the region. And the third one is obviously mangrove planting and restoration of mangrove forest. But how about if I give you, if we're talking about the solution that we can get these three things at once by doing this type of project, which is by using the GI tubes or geotextile tubes as a low-crested breakwater structure. And how is that possible? I have this picture for you under the slide, in the bottom of the slide. So this is the GI tubes. These GI tubes will serve as a low-crested breakwaters. So the first one, we making the structures like the breakwaters. We have already the structures. And the second one, we can do the beach nourishment. How is that possible? Because the GI tubes will serve as a low-crested breakwater. So when it's the high tide is happening, the wave will overflow the GI tubes and form the deposits behind the GI tube structure. So the deposits will be trapped and form a deposit accretion, so resulting in increasing the shorelines. That's the number two. We don't need to adding new material from outside the region. It is actually formed naturally from the process. And the second one, mangrove planting and restoration, of course, because GI tubes is serving as a low-pressure breakwater structure, it will reduce the wave energy that comes to the GI tube. So the wave energy behind the structure will be relatively low, and the wave will be relatively stable, making it easier for mangrove to sustain, and it will be an ideal environment for enhancing mangrove growth. And how are we going to build this geotextile tube structure? So basically, geotextile tubes is a tubes made of geotextile, obviously, and you can fill the tubes with any kind of materials mentioned: sand, slurry, mud, tailings. You can fill the geotextile tubes with any type of materials that you want. And obviously, the ideal one would be sand, because it fastens the filling process. It can settle quickly and has less dimension reduction due to settlement, because it is a very ideal material. But because we are dealing with the coastal abrasion in the muddy coastline, and it is hard to find a good sand as the filling, and we often need to transport the sand from outside the region into the coastal area, and it is not easy to find sand. We are going to use locally sourced slurry to fill the geotextile tubes or the GI tubes. And how can we do that? Actually, as you know, that slurry consists of small particles of fine clays. So we need, actually, you can just fill this slurry inside the GI tubes, but it will cause you the problem, because the time of installation would be very long, and it will, due to the longer process, you will form like a slurry cake inside the geotextile tubes. So it will be decreasing the dewatering ability, so you will not get the optimum height of the geotextile tubes that you want. So we need to form a larger flocks quickly by using the flocculation process aided by polymer here. So basically the idea is to pump the slurry into the geotextile tubes, but we need to do it faster, and we need to make a larger type of material. So we are doing the flocculation process during the pumping of the filling. So here is the project area here. We are going to install the GI tubes here. It is located in Mundu Beach, Cirebon, Central Java. And it is a muddy coastline. You can see here is the mangrove line. And the rate of shoreline change due to erosion along this type of coastline, especially in this region in Cirebon, can reach up to 78 meters per year. So the goals here is to protect shorelines from abrasion, and at the same time, we are going to promote mangrove growth. So the problem here is in this area, it's not easy to have a good co-sand as filling material. So we need to find a solution to fill our geotextile tubes with sludge, with locally sourced sludge. So the solution here would be sludge-filled geotextile tubes, or from here now on, I will just address it as a GI tubes. This is the design that we are using. We are using the GI tubes with 5 meter circumference and 1.3 meter design height, because it is going to be filled by slurry. Of course, there will be some settlement, some consolidation, and the settlement would be estimated around 0.4 meters. So the final height is estimated to be 0.9 meters. This is the thing that you have to predict when you are using slurry, that you have to think about when you are using slurry as the filling, because you won't get the full 1.3 meter design height. You have to consider also the settlement that is going to happen to the filling inside the GI tubes. So because of this area is actually a very soft deposit, so we are going to first install the bamboo piles. It's 3 meter deep. Only for the platform, and we also install some bamboo here and bamboo mattresses, and on top of that we are going to install we installed appendix, kind of a structure to prevent scoring, also made from the same material. And on top of that we have this GI tube structure, and each GI tube has a length about 20 meter, and it will be installed 3 GI tubes, so the total length would be 60 meters. Okay, this is the look of a typical installed GI tube. So we are using special material here. We are using double-layered needle punch staple fiber polypropylene geotextile with double-layered, the white one and the beige one. Why we are using this type of material is because it has a very good permeability ability, while at the same time it has a very small opening size, and the tensile strength is about 60 kilonewton per meter. So we are hoping this material, this structure, could retain the sludge inside, and not allowing for the slurry or the sludge or the small particle to go outside of the structure. But the problem is because slurry contains fine clay, what is it, smaller than 2 micrometer. It is obviously smaller than the opening size, so we need to do the flocculation process to make a bigger blocks. So prior to the project, we are doing the sludge yard test in the lab to find out the right dosage, the right formulation to do at the site, because we need to find the optimum kind of formulation. So the polymer that we are using here is anionic polymer type R1001, and we are going to use 0.2% concentration. This is the properties of the polymer. We are testing for concentration of slurry, a different kind of concentration of slurries and different kind of dosage. And finally, we have the optimal formulation consists of 20% slurry, and with 0.2% concentration, we have the dosage range between 150 to 200 ppm. And the recommended on the lab is actually 175 ppm. This is the result, and this is what we are hoping to form inside the GI tubes. So this is the construction process. We have to make this kind of setups on site. Of course, in the middle is going to be the area for the GI tubes. This is already installed the bamboo piles, and it's already installed the bamboo mattresses. And on the left side, we have this flocculant mixing tank. This is where we are going to dilute the concentrated polymer into 0.2 concentration. And on the right one, we have the slurry holding container to condition the slurry to meet the criteria, which is 20% of slurry. And this is the schematic that we are doing. We are diluting the concentrated polymer using seawater to reach 0.2%. And we are going to pump it using the dosing pump here to meet around 150 to 200 ppm. And on the other side here, we are going to condition the slurry to meet the 20% of slurry criteria and contain it in a slurry holding container, and it will be pumped in by using the slurry pump, and they will met at the static pipe and will be pumped directly to the GI tubes. So what happened here is that the turbulence, as you know, that the flocculation process actually make the bigger flux from, the turbulence and stuff. So by using this kind of method and the high pressure pump, the turbulence and pressure generated during the pumping will facilitate the formation of floc particles within the GI tube. So the floc particles will form inside the GI tubes when we pump these two materials together. And the construction process is actually consists of 3 fillings period. The first one is initial filling. We are going to fill until the design height, and we let it dewaters, and we fill it again and let it dewaters, and we do the final filling and we let it to consolidate. On the right one is the picture when we are doing the filling. This one is the first GI tubes, and the next one is the second GI tube. So we are going to fill this one and then let it dewaters and fill this one and let it dewaters and go back to the first one, and so until we reach the final height of the second refilling, and we let it consolidate. This is the result, the settlement of the GI tubes. The final height of installed GI tubes actually range from 1.3 to 1.4 meters. This is normal when you are constructing GI tubes. It sometimes goes higher than your design. It's normal. And we have here 1.3 to 1.4 meters. And as you can see in the graph, it progressively having settlements, and unfortunately we only monitor it until 100 days, and at 30 days the height decreased about 84% from the original height, and at 60 days the height decreased to 69% to 1 meter, and after 100 days the height decreased to 61% of the original height, resulting in the final height about 0.8 to 0.9 meters. So it's not many difference from the design. So this is the thing that you have to keep in mind if we are going to use this kind of system, that we have to allow for the structures to consolidate, and we have to realize that there are going to be settlements of very high settlements. So you are expecting to have a kind of 40% of reduce in height. That is the thing that you have to keep in mind. And the next result is the performance of the GI tubes. On the left one, you can see how water discharge from the GI tubes. So the double layered geotextile material actually have a very good performance in dewatering sludge within the GI tubes. As you can see maybe in the picture, only the clear water comes out from the structure. It means that there is no particles that goes out of the structure. So the structure actually contains the sludge very, very well, and just allowing for only the water to come out. And the second one here is after we are doing some kind of observation, we found out that there is no sign of damage. We do this in 2024. although, as you can see, maybe you're not seeing it very clearly, there are some marine organisms attached to the GI tubes, but actually they did not cause any damage to the material. And actually the material, if you want to see it from the Google Earth or so, you can still see the material formed very well. So it is proven that the material is still durable even after 2 years. And the next one, and the most important one, is we are going to see the effect, what is it? The effect of the installation of the structure. 7 months after GI tubes installation, you can see here that very clear deposits is already there. You can notice that is accumulation of sediment observed behind the GI tube structure. This is the GI tube structure, and this is the sediment. So it confirming the effectiveness for the GI tubes in reducing wave energy and promoting shoreline accretion. So on the right side, it's actually, I just got it yesterday, the image from August 2025. This is the original line, and this is the original line, and this is now the new line of mangrove. So before, our monitoring in August 2024 showed the sludge still remains solid. It means that the structure still well performed. And from this picture, you can see that behind the structure, you can see that mangrove actually grows fast and strong here. You can notice the extension of the mangrove line over 50 meters here. So this is the conclusion. The first one, the combination of the GI tube materials and the consolidated sludge actually created a highly effective low-pressure breakwater structure. And the second one is the material, the double-layered non-woven geotextile. The GI tube materials is actually very, very good. It has the characteristic that enables the materials to effectively contain the sludge within the GI tubes while promoting rapid water drainage. So we have this good dewatering efficiency. So the third one is by utilizing locally sourced sludge, we can have a sustainable solution in mitigating coastal abrasion in muddy environments. I think that's all. Thank you, Roger. We'll get back to you.
Thank you so much. That was fantastic. I'll pass it to the next speaker so that just conscious of time, I'll just do a really quick introduction. Sarika is a research scholar. Let me just share my screen. I'll do that. Yeah. Share it. Yep. Sarika is a research scholar in the Department of Civil Engineering at the Indian Institute of Technology, IIT, Guwahati. Her research primarily focuses on geotechnical problems associated with geotextile reinforcement, slope stabilization, characterization of soil, geotextile composites, debris flow behavior, and the micromechanics of granular materials. I'll leave the rest to later. I'll just let her kick on because we are running over time. So you can take over, Sarika.
Thank you, Roger. Is it visible?
Yes, I can see.
So thank you, Roger, for the introduction. Hello all, I'm Sureka. I'm doing my PhD at IIT Guwahati. So the topic of my presentation is investigating the dual role of geocells in slope stabilization as reinforcement and fascia. So in here, I'm going to discuss the behavior of geocells against seismic loading because where I'm working at, we have earthquake prevalent every once in a while. So geocells are a type of geosynthetics in three-dimensional form. It has honeycomb structure. In India, it is mostly made of high-density polyethylene. So it has various applications, starting with a foundation for embankment or footing, and it helps in improving the subgrade strength of the pavements. And also it helps in reducing the erosion of slopes against rainfall. And also it is used for slope stabilization purposes. So my focus is on utilization of geocells in slope stabilization purpose. So there are different reinforcement mechanisms for geocells. The first and important one is confinement mechanism. The vertical walls of the geocell pockets provide confinement to the infill soil. And the second one is the membrane mechanism. So the whole of soil infill geocell layer under tension, it will give a membrane effect upon bending. The third one is the vertical stress dispersion mechanism. So in here, the applied vertical stress will be dispersed to a larger area, and hence the stress magnitude is reduced. So these are the three important reinforcement mechanism of geocells. And in my study, I'll be showing you the responses of two models where geocells are used as reinforcement and as fascia. So on the left, it is just the reinforcing capacity of geocell layer, and on the right, the soil infilled geocell layers when stacked one upon the other. It acts as a retention system. So in here, so these tests are conducted in the check table where artificial earthquake is simulated. So the responses are recorded using these instrumentations. So we used piezoelectric accelerometer for acceleration response, and the displacement of the model faces are recorded using non-contact laser displacement sensors. And lateral earth pressure exerted by the backfill as well as the infill soil is recorded using pressure transducers, and the tensile or strain developed in the geocell walls due to the applied seismic loading is recorded using strain gauges. Locations are given in this model layout. So this is the shake table setup that is available at IIT Guwahati. So it has a loading platform of size 2.5 cross 2.5 meter with a payload capacity of 510. So it has a stroke limit of plus or minus 500 mm. In total, it can go move till 1000 mm. And it has the acceleration range of plus or minus 2g with the frequency range of 0.5 to 10 hertz. And upon this shake table, one perspex tank, it is as shown here, is fixed to the shake table using a rigid connection. And inside that, the models are constructed. Now, the perspex tank size is 1200 cross 600 cross 1000 mm. And it has, in the rear wall, it has a styrofoam sheet, which helps reduce wave reflections in the model. And the front wall is left open to for ease in construction of the models. And one of the side wall is marked with 5 centimeter mesh for post-processing and visualization of we can measure the deformation of the model using these markings as measure reference. And the tank base is covered by sandpaper in order to induce friction to the model base. Further, there are various type of geocell sizes that is available in the market. For experimentation purpose, we have used 100 mm cell height and the well length of 330 mm. Both the infill and the backfill, which is the sand inside the geocell pocket, as well as the mass that is retained by the geocell fascia, is composed of sand, which has a peak friction angle of around 47 degrees. Now, two earthquake motions we have given multiple seismic motion as well as sinusoidal motions to the models. Here I'm going to discuss about the two earthquake motions, Indo-Burma and the North Ridge one. So Indo-Burma is on the, it has least PGA of 0.08 G, and North Ridge has a high magnitude PGA of 0.56 G. Now, this is fed to the shake table. So in general, the input that is fed to the shake table and the one that is replicated by the simulated by the shake table will not be identical because of the system's limitations. So one accelerometer is fixed to the top of the shake table so that we have an idea about the acceleration of the seismic waves that is propagating into the model. So in here, the acceleration time histories are presented for both the Indo-Burma as well as the North Ridge motion, and in case of both fascia as well as the reinforcement model. So the left one shows the response time histories for table recording time histories for Indo-Burma motion. So in here, we can see that there is a difference in case of table response for between reinforcement and the fascia models. Now, due to the variation in the geocell configuration, the distribution of mass in the shake table varies for these two models, because of which it has developed an additional noise in case of fascia. Whereas this kind of phenomenon is noticed only in case of Indo-Burma motion, where the PGA is very less. In case of a significant higher PGA like North Ridge motion, this effect is not noticed. So in case of so here the figures of reinforcement as well as the fascia models pre and post shaking is given. So at first we thought this reinforcement model will not be at all possible, as there is only partial confinement and the sand will move out. But upon construction, we realized that it is possible. So the left one shows the figure of pre-shaking reinforcement model, and the right one gives the failure model after the shaking. During shaking, some of the sand mass has rolled down towards the toe from crest, as well as the sand that is sandwiched between the reinforcement layers, due to which certain settlement of 4 centimeter is noticed in the top reinforcement layer, which can be seen. We can see the fascia models before and after shaking. So in here, the failure occurred in a way that there was loss of connection in the boundary, due to which the infill as well as the backfill moved out, and due to which the soil mass near the fascia underwent settlement. Now coming to the acceleration amplification that is recorded in the fascia as well as the reinforcement configuration. So Indo-Burma motion, as being the lesser PGA earthquake, so it has amplified irrespective of the models, and in case of the higher magnitude motion has de-amplified. So when we look into the difference in the responses, so it can be seen that the reinforcement model forms the extreme, be it amplification or de-amplification. It forms the extreme of the responses in amplification factor along the slope elevation. Whereas introducing fascia has increased the stiffness, and also it has reduced the amplification de-amplification bandwidth. So this amplification is calculated. It's a ratio of PG of the output motion or response that is recorded with respect to the PG of the input. And proceeding to the displacement response. So three displacement transducers are placed to measure the displacement of the model faces. So in case of fascia, the response is corresponding to the the transducers are pointing towards the geocell pockets itself. Whereas in case of reinforcement model, the bottom two transducers are giving the response of the geocell layer, whereas the top one is focusing towards the response of the crest, which is made of only sand. So the response can be distinctively seen in this displacement time history, where so the top one is for the reinforcement model. The maximum displacement was noted in the middle reinforcement layer of about 34 mm. And so the top one, the one time history on the positive side of the axis, it shows that is corresponding to the crest, which is of the sand. So it can be clearly seen that there is a distinct displacement recovery between peak and residual for the locations with the geocell pockets, where only sand is present, the peak and the residual are the same. This is because during shaking, some of the sand mass has rolled down towards the toe, and because of which the model has caved in at that crest. And in case of fascia model, the displacement recorded are very much lesser than the one that is recorded in the reinforcement. And the displacement trend is like there is maximum displacement at the crest, and it reduces towards the toe. And you can also see the displacement recovery, which is the difference between peak and the residual displacement recorded. Now, proceeding to the strain development in the geocells under the earthquake motion. So here only the response corresponding to northwest motion is given, because the one recorded under Indo-Burma earthquake was very negligible. So in case of strain development, comparison is made between the geocell layers that is present at the same elevation between the reinforcement and the fascia models. So the strain development is in such a way that the maximum strain was developed at the frontal geocell walls, where there is no confinement on one side and there is infill sand on the other side. As proceeded towards the interior, the strain decreases. Now, coming to the upper reinforcement layer and its corresponding one in the fascia. So in these responses, we can see that few curves are there in the positive side of the axis, and some are there in the negative side. So the positive side shows the tensile strain, and the negative side shows the compressive strain. So towards the upper elevations, only the frontal geocell wall was undergoing tension, and the rest of the geocell walls are undergoing compression due to the movement of the backfill towards the fascia, means towards the outer. So due to which we can see some responses in the negative side of the axis. And this is with respect to the strain that is developed in the geocell walls when looking into the lateral stress that is exerted by the infill soil as well as the backfill on the geocell walls. So this is corresponding to the infill stresses. So the infill stress that is exerted onto the frontal geocell wall is maximum for fascia. This is because there is uniform confinement throughout the slope elevation in fascia. But in case of reinforcement model, the confinement is only partial. So some of the sand mass moved out, due to which there is only less incidence of lateral stresses onto the frontal geocell pockets, frontal geocell walls. Now, when we look at the lateral earth pressure that is exerted by the backfill, here it can be seen that the compressive strain, whichever was seen in the previous slide, that is supported by the higher lateral stresses in this figure, in case of reinforcement models. So this indicates that the backfill is pushing the reinforcement layer out, like the geocell layer outwards. And in case of fascia model, it was noticed that even though the higher lateral stresses were seen, are seen in the exerted onto the geocell walls, only lesser strain was taken by this geocell walls. This is because of the higher stiffness of the system and due to the uniform confinement throughout the slope face. Then these are simulated numerically as well to look into the hysteresis behavior of the model phase as well as the backfill. So wherever the monitoring points are located in the geocell pockets, the stiffness is higher. So like we can see that the shear stiffness in the hysteresis behavior is higher, where the monitoring point is in the sand alone. So it has a relatively lesser shear stiffness. And in this, we can see that the hysteresis is not a loop, it's kind of a line. This is because of the higher stiffness of the small models. So in order to instigate nonlinear behavior in such smaller compact models, we have to scale down the materials that we use in the structure, properties of the materials that we use in the models, as well as it is necessary to scale up the motion intensity, the magnitude of the motions. Now, like when we look into the response of the backfill, so due to the increase in stiffness of the system in fascia model, there is higher range for shear stresses and shear strain, whereas in case of reinforcement, that provision is very much lesser. Now, in conclusion, so in case of reinforcement, due to the non-uniform confinement, some part of the model was vulnerable to cave in, and since the sand was sandwiched between the reinforcement also moved out, there was settlement notice. And due to uniform confinement in the fascia, there was lesser displacement, and we could see effective retention. In some parts, a geocell layer moved outwards due to the absence of interlocking friction above and beneath the geocell layers, whereas this was very effective. The locking interfaces were present in case of fascia. And also, strain concentration was noticed wherever geocell layers are present. But again, it was uniformly distributed throughout the fascia. Now, there is an advantage of reinforcement because these geocell pockets proceed till further into the backfill, due to which there can be more stability. But due to the absence of fascia, this model was a failure. Now, when implemented along with the fascia, like both the reinforcement and fascia model combined together, the cons gets cancelled out, and which it will the system will function effectively under dynamic loading conditions. So these are the results concerning to the combined effect of fascia and reinforcement models are in our further works, which is under which is being communicated. Now I thank my supervisor for guiding me throughout and supporting me every time. And also I thank Strata Geosystems for supplying geocells for our research. Thank you.
Thank you very much, Sarika. And it's a round of applause to all three presenters who were selected by the executive committee from ACIGS for being some of the best presenters that was showcased at the GeoAsia conference in Melbourne, and we had a number of really fantastic speakers at the Geo conference. So these three speakers here were some of the best. So thank you all for joining. Was there any questions before we wrap it up? I know we are running over time. If you do have any questions, please come off mute or put into the chat. I'll give a couple of minutes before we conclude. If there's no questions, make sure you jump on the ACIGS website, fill out the student membership form, and apply for some internships or job shadowing if you're interested, or join the committee or the group if you are interested in organizing future conferences and events and being part of the network that we have here in Australia and Asia. Thank you all. I'll just take a quick screen grab if you all permit. If not, let me know. And I appreciate all of your attendance. Thank you all. I'll wrap it up here.